Okay, hello, thank you very much for having me here. I'm Avishai from Tel Aviv University, School of Mechanical Engineering. I'm going to talk about two things. One is a work we've done a couple of years ago about multi-agent systems and RL and stuff like that. And then I'll put a president here, so I'll talk about human-robot interaction a bit. And then I'll put it in the RL perspective, but so I'll start. Both this one. So when we are considering model-based reinforcement learning, and we all know the advantages of model-based reinforcement learning, so you have very unstructured environment, complex systems, and we all know these kind of stuff, and many uncertainties. If we're talking about low-cost systems, 3D printed systems, a lot of uncertainties exist, and with the complex environment of real-world tasks, these are complex, so we don't have analytical models. Realistic simulations are usually unavailable or very complex. And so it's hard to acquire a good model in order to train our RL policy. So usually what we do is we approach it with a database model. We train the data, we collect a lot of data from the real system, and we train a database model, some kind of neural network. And they are able to learn these uncertainties and complexity of the world. And in our lab, we've done it a bit, and we've done it in robotic hands. These are 3D printed robotic hands that are very uncertain because of their springs and wires and uncertainties. We've done it in human-robot interaction for wearable systems, and we've done it for routing wires. But these systems are, so usually we collect a lot of data, and this is very hard to transfer so if I build a new hand, it's very hard to transfer the model. Okay, and the challenges are data, and more data. As we know, these models tend to be very bad data hungry, and it's very expensive and even dangerous. We have a robotic arm that needs to train a lot, can be very dangerous, can break something if the policy is not yet good enough, or the model is not yet good enough. So we need to collect a lot of data, and if we have different agents, maybe we have to collect data from different agents, and that's very exhaustive. As we know, Gen AI is something that we've been interacting with a lot, either with this DALI and all these ChatGPTs and stuff like that. And when we started working on these kind of stuff a couple of years ago, these kind of things were just starting to come. But less explored is how we generate data in the space, or in the space of these robotic systems. And here the image or the video can be a little bit distorted, it's okay, but if the synthetic data for the state space is not good enough, then it's probably useless. So we initially started working on robotics for underwater exploration. Group of robots working on underwater exploration, but because it's easier, we started with these kind of systems. We built these kind of very cheap, low-cost robotic. We got ground robots, micro ground robots, and the idea was to have them reach some target or do some tasks together, and a decentralized policy. Basically, because it's underwater, so each agent can only observe its near area, regional area, and know just a limited state observation of the environment. And we started with analytical models, and because of these low-cost systems, the analytical models don't have the ability to understand the uncertainties of the system, and a simulation is not available. So what we did is let's learn a model. Let's collect a lot of data and build some kind of MDP model. But we needed a lot of data because each agent here is a little bit different, and it's very exhaustive. So let's say, okay, we thought about something is missing here. Okay, then I'll put animation there. So what the idea is here, okay, let's collect a limited amount of data, not a lot of data, a limited amount of data. And one option is to just go ahead and train the model with, this is a model. But less important, we did some kind of work on some kind of architecture for a transition model that was better than others, but that's less important. We can take the data and just go ahead and train this model, or we can use a generative adversarial network in order to generate synthetic data. And the claim was here, and with this we can have a simulation of the system. And the idea here, or the argument was here that, okay, we could collect a lot of real data and have reach some kind of low error, or we can use the data and better to invest the data in training a generative model and then go ahead and generate synthetic data as much as we want. It's almost free. And this was I can't say a relatively new idea because it was a few years ago, but it was less explored. And indeed, if we take the real data and train it directly the model, or train it the generative model, and then use the model to train the transition model, you reach the same accuracy. So it's at least the same accuracies. But if we look at the data, we can reduce, this is basically a comparison between how much we use real data to train the generative model and how much synthetic data from that generative model, what accuracy we receive. And we see that with only about 25% of the real data, we reach the same accuracy as just using the entire data to train the real model, to train the model. So it's better to invest the data in the generative system. It's better to invest the real data, a limited amount of real data, in the generative model instead of going ahead and training the real system. And this is an example with one agent. Here it's an example. So this is the simulation. After we collected a lot, we trained the model. We basically ran a lot of episodes simulated. Each agent here is running the same forward model we trained with the synthetic data. And after we do that, we deploy it on the real system. Come on, where's the, okay. So here these agents are working together to reach the target. Of course, when we reach the target, the system is a little bit unstable and they start to move around the target. And do it a few times, and it's kind of nice, but it's not something new. And the next step was, as I said, we wanted to do this underwater, so we bought a pool, and after we swam in it, and we built this kind of robotic fish, planar robotic fish with buoyancy on top, and we trained them. These oscillations here are some kind of symptom of collecting data that is arbitrary and random, and we weren't able to solve. I mean, we can solve it, but it's less important. It's just originating from the way we collect the data. But still, they move between targets and work together. Unfortunately, we didn't have more fish in order to have this. Okay, so that was for a multi-agent system. We've been doing also work on gesture recognition, or natural intention recognition. Basically, we observe how humans interact with each other, and we say, okay, this guy is standing a bit far from this guy, and in order to direct him to do something, he can point, he can apply some gestures, and also maybe later add some verbal communication in order to provide context. And we want to mimic that to a robotic system, and this is part of the Human-Robot Interaction Consortium. And so, of course, we want to be able to interact with these robots naturally. So a frequent user can just talk to him or move, okay, go there, bring me that. Like we talk between each other. And if we put it into current events, so currently soldiers working, we've seen a lot of videos from the IDF spokesman, and we see a lot of soldiers holding remote control in the battlefield and looking at the remote in order to manipulate a robot to somewhere. And this puts a lot of cognitive overload on the soldier. He also needs to observe the environment, it's a hostile environment. And this is only valid for male soldiers. Female soldiers can do two things together, both at the same time. But we males cannot. So this is work with Elbit, and Elbit says, okay, we want the soldier to hold the weapon and not have a remote, so we can. The idea is how to direct the robot naturally. And when we observe the literature and gesture recognition, we've seen two categories. One is close range. You're sitting in front of the computer, doing some gestures. This is nice and cool, but it's not very practical for a human-robot interaction. Long range, what is called long range, is about 5, 6, 7 meters, not that much work. It's called long range, and usually, usually indoors. We haven't seen work that does this outdoors. And our goal was to do this in what we called ultra range, because long range was occupied by 7 meters, so we call it ultra range, and at least 25 meters, and outdoors, indoors, in various environments. And just to put perspective, if we do that human perception, we took a few people, different ranges, and we've seen that it's not easy to identify gestures from up to 25 meters. And if we observe the existing models, so OpenAI, MediaPipe, and these kind of stuff that do skeletons, they practically cannot work in these ranges. So we've devised a model, basically two models. One is taking the image of the user, improving the super resolution model, improving the resolution of the image. So other super resolution models did not work, or did not specifically effective for deep time and looking at these finger features. And then another model based on the graph convolution networks and vision transformers in order to do the recognition. And you can see the success rate was very good. If we look at the distance, the success rate was distance, you can see an average of 98% success rate. And the test here is a different environments, different people on directive gestures. And you can see some few examples. I cannot see anything there, but the robot was able to. These are a few examples. Outdoor, indoor. Let's jump here. You have no. No. Nope, I cannot. Okay, so there are various environments, even I'm modeling here. The problem here is data. So my student Eran here catch anyone in the hallway, anyone in the lab. Okay, let's model, take a lot of images. We collected a lot of data in order to achieve very good success rate. But here comes the generative model. Let's generate data in ultra range. So we explored, again, GANs. It wasn't that successful. I'll show the results. So we used the fusion models. And with diffusion, we're able to constrain the gesture and the distance. So we are able to say, okay, I want an image of a person standing in 22 meters with pointing or saying thumbs up. Okay? Basically based on diffusion models with a few tweaks of us in order to improve the quality. And here we also collect a limited amount of data. We had some data, and now we don't have to collect a lot of it. So here you see a few comparisons. This is our model, and this is these are synthetic data, synthetic images, okay? And you can see here different guns, conditional guns, and here is the R model. These are my students, but still they're synthetic. And even the quality measures are quite good. And here again, you can see here, this is the older curve of collecting real data. And if we collect the real data and invest it in the diffusion model, we reach it very fast with only a limited amount of data to quite high success rate. And from there, we are quite high. And what we see here that is the limited amount of data is able to capture a very good distribution of the problem. This is quite interesting, and this is the power of diffusion models. With a very limited amount of data, it's able to capture the most of the distribution. We also done work on pointing, so estimate recognition, but estimating the direction of pointing. This is only with real data. We'll probably explore some generative data, synthetic data to do this, but the idea here is basically with a single, I did mention everything here is a web camera, nothing, no depth camera, no anything. Just with a web camera, it's able to estimate the points we want to reach, either long distance or far distance. Okay. So let's connect this to RL. So first, what I'm trying to say here is better sometimes to invest the data in the generative model instead of just going ahead and train the real model. And so the idea here now is, and something that Golan talked about is, okay, let's do RL on this kind of system. So I'm doing a gesture. I'm telling him to stop. He's not going to stop. So I'm going to give him some kind of gesture to reward. I'm going to say, okay, bad, this is bad. And then try to loop over that and try to improve its performance. I'm going to train it, basically like training a dog to do this and to behave better than as I want, and use these gesture models as a prior, because as said here, it's very hard to collect a lot of data to do these episodes with humans. And of course, add this with, as we said, it's required to add LLMs or LLM to reward in order to add context to the behavior. Okay, credits to my students with their synthetic images, and that's it. Thank you.
We have time. We need to go back to the robots. So said you collected data and one with the simulated data.
This one?
Okay, I'm sure or any robots. Yeah. What are the kinds of robots? Are you trained? Because you started by talking about using data to learn the model, and I was sitting in the transition model.
Yeah.
You mentioned that the robots were different, and here they seem like they're heading towards some objective.
Mm-hmm.
So is this still the model? Are you still learning the model, or is this trajectory?
Okay, so maybe I wasn't clear. So we learn a model for an agent. And that model is a simulation. So here we throw it into a DDPG environment. We run episodes in RL to just learn a policy.
RL to learn policy that
the model is a simulator in order to train the policy.
But here you are rewarding an agent for achieving an objective, right?
Yeah.
So
I was focusing on the modeling and not on the learning the policy.
But the model was used to model the transition.
The model is the transition.
The data that you collected was in order to model the transition.
Yeah.
Yeah, so my question is about the synthetic data. Why do you think it works? To me, it seems like whatever data, real data we use to train the generative model, the same data we use to train the policy anyway. So why would, like it contains the same information, why would it help to generate new synthetic data? It just rehashes the same real data.
Well, we didn't see that much with GAN. GAN is not that powerful to do that, but diffusion models.
According with GANs, you said the water field data plus synthetic is enough.
Yeah,
Yeah, it's pretty powerful.
it's hard to tell. Honestly, it's hard to tell.
Wait,
Um,
you've done this with GAN.
This is GAN, yeah.
Yeah, so this is GAN. So it's just like a world model. It's just doing a good world model, and then it's training the RL algorithm on the world model that the GAN made. This is why it works. If you have enough samples to model the world right, then
But here you reduce the number of data.
yeah, this is what you showed later. So
Yeah.
if you don't have enough data, you don't have the real distribution of the world. So
Right.
you don't have enough.
Yeah, but the GAN and the diffusion model is able to learn that distribution, that are approximate that distribution.
You're
As
close
a
to the
result.
distribution.
Yeah.
You have more data.
Yeah, of course. More data is always good.
I mean, it doesn't really answer this. Like, if your answer is that it works because world models work. That's why those.
Why world model works?
It's cheaper data-wise to generate a good enough world model.
No, that's not the question. So the question is, given that the world model learns from the same data the policy group, why would this extra model have?
Because you're doing two different, one of the processes are more efficient. And the other, you're building the world, you can build a good enough world model.
Yeah.
Cheaper in terms of data.
I know, like, predicting the next state seems more difficult than predicting just policy, like I mentioned.
The process of learning this to generate synthetic data is more efficient as it's able to better capture the features you want to learn.
Which isn't much of an explanation, it's just like this stating that that's what's happening, not just explain to you all.
So that's a great
That's enough.
discussion, and we can continue that in
Thank you.
the roundtables. Thank you so much.